All right, so my name's Andres,
And my name is Ricardo Ochoa.
and for our final project, we decided to try cracking some crackme's, and our group name is Operation Antique Enigma.
Thanks for that name, Bill.
So, kind of like an overview of why we did this. We thought it would be a good way, to just test like our current reverse engineering skills, and then we also thought just by doing this, like we would improve our reverse engineering skills. So the two files we decided to try to crack were Harry's Corner and Heaven's Gate, and we got these off a website called crackmes.one, and they've got a couple files on there. So if you guys want to check them out, uh, you can check them out.
Some of the software that we use would be IdaPro, the free version, because I don't think anybody would want to pay for that just for this project. Continue, we also had a hex editor, trying to just change the bytes inside of the crackme, see what we could like change. And as well, we use pbrowse just to perform some static analysis over the crackmes that we had. And as well, for one of the crackmes, we used the online disassembler, which helped disassemble the OB codes of a 64-bit portion of one of the crackmes that we went over. And as well, we created our own VM. I used the VirtualBox. I didn't really like using the VM that the school provided, but my partner here, Andres, he worked on the VM through the class one.
Yeah, so
Uh,
uh, I ended up using the class one. Well, I tried using, I did make my own VM, but it was really slow for whatever reason. So I ended up like halfway through just using the school VM since it's faster for me. All right, so for Harry's Corner, the first thing we did was we just put it in a hex editor, uh, because that's always kind of like a good step. And as you can see here, we can see kind of some strings, right? Like asking for a password please, then approved or denied. So obviously, depending on what we enter, we'll either get approved or denied. And then we put it in PE browse, just like Ricardo said, just to get like a basic information from it, like the image base or the virtual size or the pointer to raw data. Always handy information to have. Okay, and this is what it actually looked like, what the program actually looked like when we put it in IDA. And as you can see, just from not running anything, just by performing some static analysis, you can see like it looks like we're pushing the string and then we're calling some functions and then looks like we're testing EAX, and depending on the result of that, we'll either take the approved path or the denied path. And here we just ran the program and we typed the password as password and we got denied. So obviously that's not the correct password, but you guys kind of get, the idea of what the program's trying to do here. We're trying to find the password or the correct password, and so that way we can get the approved message. And then after we kind of did, some analysis, we went through and changed some of the functions. That way it made a little bit more sense. So like this print function, since really after once you push this after this call, it'll just print out, the string that you pushed here, or that you have in the RDX register. And then we also changed this call right here to user input because it's basically just like acting like as a scanf. Like once you step over this call, the program will always be waiting for our input. And then we changed this call right here to start of comparison because this is kind of what starts the comparison of our input to the correct password. And we'll kind of see how that looks here in a second. So here's the inside of start of comparison. As you can see, looks like, we're setting up some arguments. We're loading some arguments, and then we're going to this call right here, this function call. And this is what the inside of this looks like. And as you can see, we're using this call right here twice, and then this call, and this call right here, this one that looks all kind of strange. This one is where we actually kind of take a look at like the real comparison, but we'll see that later in the demo. It'll make more sense. All right, y'all. So I'm just gonna demo real quick the Harry's Corner file. Yeah, let's see. So as you see, I kind of got the same setup here, basically. So let's just run the program real quick and step over this. Now, as you can see, it's waiting on my input. The program can't like debug or anything anymore. So I'm just gonna type a random password in, and then here in RDX, we'll actually have the address of the correct password. So as you can see, this is the value we have, but this value is basically the address to the correct password. But this isn't the correct password though, so hopefully that makes sense. Like this is just the address to the correct password. Let's go back to main here and step one more time. And as you can see in our CX, we'll have our password, the address to our password. So you can see 1, 2, 3, 4, 5. And now let's step into the start of the comparison. And here we're just saying some arguments, right, using the RDX and RCX registers. So the registers that, have our password and the address to the correct password. So let's just run this real quick. And let's step inside this function. And this kind of the block that I had from the slides. And this function is where we actually found at least the first time we found the password. But after going back and kind of debugging this again and just analyzing the program again, we realized that the password really is available after in this function. Like we'll actually load the password here in this function. So let's do that real quick. So step over these, and we'll just send some arguments right here. Step over and step into this. Then, as you can see, the line we really care about right here is this line. This is where we're actually load the password. So let's continue to debug this, and we'll just send some arguments up for this call. And once we hit this call, we'll end up returning 1. But because this this whole function call really is used again, right? This unknown lib name 11. We use this again for our input, but here when we're analyzing the correct password, we'll end up returning 1, but for our input, we will return 0. So right here in the comparison, right, it's comparing with 0f, and we'll actually have 1f. And I'm not entirely certain how we have 1f, but I know we'll always have 1f when we're looking at the correct password. So once we step here, as you can see, we're gonna have 1. We're gonna return 1. So in REX we have 1. And then let's step a couple times, and we'll end up in this block. As you can see, we're in RAX we loaded like what we had previously had earlier. As you can see, it's just the address to the correct password. See, we still have these in these registers as well. And we step one more time. And now in RCX, we'll have the actual password to the program. So if I click this, as you can see, it's this whole kind of string from this first U to this U. Doesn't include the 0. It's one of the mistakes we did when we were working through this file. So it's this U to this last U that is the actual correct password. But like I said, originally we didn't get it from here. We didn't realize it. It didn't hit us at the moment. It took like we didn't realize it until the other function call. But let's continue here. So once we step into here, and we'll end up just having RAX is going to have the same value as RCX. Return. And as you can see, RAX and RCX have the same value. And now we'll end up doing the same thing for our input. So if I step a couple times, see, RCX should have our password, as you can see. Let's go back, but I won't step into this actual function call again though. So I feel like you guys probably kind of understand what's going on there. So we'll step over to that, and then here in these on this section, we're just kind of loading like the length of the password. So if we step a couple times, R9 will have the length of the correct password, which is 1B, which should be 27 in decimal. And then R8 will have the correct password. So if we click on this, as you can see, let's go back. And then RCX will have our password. And then if we step one more time, RDX will have the length of our password, so 5. And then we'll move here into like where it actually kind of compares the passwords and stuff. So step into this. Like I said, this is where we realize it. As you can see from the comments, it's kind of the same as the other code earlier, but basically just loading the length of the correct password, and then the correct password, and then the length of our password of our input. Then RCX can have our password. But this is kind of where we realized it. The first time we were debugging this file and trying to crack it, it was in this area. We didn't realize it in the other area. But basically, what this program is going to do is RAX will have 1B, or the length of the actual password. I know right now it doesn't, but once we step through, it will. But if they are not the same, then we'll go to this block right here, and we'll end up returning 0. But if they are the same, then we'll go to this call, or this block, and then hit this call. And then as you see, we're using mem compare. And if the strings are equal, then we'll return 1. But if they're not, which in our case they're not, it'll return 0. So let's step through this real quick. See, as you can see, RX is gonna have 1B, and then we'll have 5. And we should hit this block since they're not the same length. And then we'll end up returning 0 since we don't have the correct password, or I didn't type the correct password. And now we should go into this denied block. And if I step over this, so we're printing it out. Go back to the program. As you can see, we got denied. So now let's try it with the correct password. Let's run the program again. Let me step over this. Let's wait for our input. Let's step over, step into. I'll let this run. Step into here. Run again. Just so you guys can see kind of the logic of the program again. And we should enter this area. So if we keep debugging here, you can see RAX will have 1B, and then we'll have 1B. So we should enter this block, as you can see. Then we're setting up the arguments to the function call. We'll go in here, and then we'll end up hitting this mem compare. Then we'll test the EAX, and since we entered the correct password, we're gonna get 1, so we'll end up returning 1. So we turn out of this call, we should go to this approved area. As you can see, step a couple times. And we got approved, so this is the correct password. So yeah, like once you kind of understood the program, at least kind of the main logic, like for like it all kind of clicks, like it's not too difficult. So hopefully you guys kind of understood what I was trying to, kind of our process that we kind of went through here. So yeah. All right, so for the intermission, we'll be taking a look at the second program.
We will now be looking over the second crack me that we worked on called Heaven's Gate. We'll load up our VM, and I already have it set up with the necessary software such as our debugger, the hex editor, and PExplorer. These are the software that we will be using to solve this crack me. The first thing that we did was run a program, see how it would function. It does display a message saying please enter a valid key. We'll input a random set of characters and hit enter. Right away it does say wrong, so we did get the key incorrect, bummer. Hit enter again, it will close out of it. From here, typical crack me, nothing too crazy. What we did next was put in the PExplorer and see what kind of information we could get out of it. The important thing out of here that we did get is that it is a 32-bit executable program. This information will be useful later on. Now the next thing is loading up into IDAPRO. Once we have the program loaded into IDAPRO, we did go to the strings section. The reason for this was because we wanted to check if any of the messages that were displayed in the program were saved under strings. And we did notice that it was. We have wrong here, and as well please enter a valid key. So we will be going to this location and see what is happening. After following where these strings are being referenced from, we get to this section of the program. We can see that it asks us to please enter a valid key, and as well our strings of correct and wrong, which are being called and determined by this comparison right here. For whatever value is loaded here, it will determine if the key that you entered was correct or wrong. So we must find who is loading a value into here. So now let's follow to where else this is being referenced from. Thankfully, it is only being referenced in one other section of the program, so we will go ahead and go there. Now that we are here, we can now start analyzing what is going on, what is determining this value inside of the register EAX to either be 1 or 0 and displaying a correct or wrong message after the key input. So we scroll up a little bit and we see that it is part of this function here. So let's put a breakpoint at the beginning of this function just to see what happens once we run the program. Now that our program is up and running, we want to insert a sequence of characters that we will be able to use to track throughout the program, such as a number sequence of 1 through 9. And we want to just hit enter. Now we can see that our program stops at our breakpoint, and if we go through, it does some stuff, but the most important thing is that it clears up EAX, EBX, ECX, and EDX inside of the function when stepping through, which is going to be very important. Now it starts loading some values inside of the lower byte registers for EAX, EBX, and ECX here. So after each step through, we now want to check the registers. We see that 33, 34, and 37 are loaded. Remember when I inputted the sequence of numbers 1, 2, 3, 4, 5, 6, 7, 8, 9? Well, now we could check something out by going to where these bytes are at, and we get to this location here. We see that 31, 32, 33, 34, 35, 36, 37 are being saved in this location, and which is being loaded here. Now these are the ASCII characters in hex for the input that we just provided of the numbers. So 31 hex will mean the number 1 on the ASCII table converter, and it'll be the same. So this is 2, this is 3, this is 4, this is 5, this is 6, 7. So we could assume that our program only takes 7 characters for the key, which is going to be very useful information. So now let's just go back to where we were at in our program, and we just continue stepping through. We now see that some of the registers start getting loaded same way. Now we have 35, 36, 31, and 32, which are the ASCII hex values of our characters from 1 through 9 that we inputted in our key input. So we continue going through the flow of the program. We see it do something very weird. So let's just continue stepping through. And once it hits this return far from procedure, it completely throws off the debugger and it goes to this location. We open up the program, and we see that as soon as we step through it once again, it'll display it wrong. So what happened here? Let's take a look. We are back here at the same function that we were just at. Right here we have the return far instruction where it threw off the debugger. This is obviously a obfuscation method to disrupt the flow by manipulating the stack, since the return far instruction is used for returning from a procedure across segment boundaries. As well, when researching about this issue, we came to find out that there is a technique called Heaven's Gate, which ironically our program is also named that, which involves the ability, to execute 64-bit code from within a 32-bit process on a 64-bit Windows system to further obfuscate the program's flow. This was also talked about in Module 8 from class, which I found to be interesting in this situation. Using the knowledge in the Module 8, we know that in a 64-bit mode analysis, we will see the program perform offset operations by adding a byte offset to the current location the program is currently at in a moment. This can be seen inside the function right before it throws us off. So let's analyze this portion of instructions. So we are analyzing this set of instructions here. I put a breakpoint just so I could get back to this location after running my program again. So first we see that there's a push to 33 to the stack, which is this one right here. And then once it makes that push, it goes to the next line and makes a call. Every single time there's a call that's being made, the address, the return address is going to get pushed to the stack, and which is this one right here. After this line, it'll go to this next instruction, which manipulates the return address by adding 5 to the stack, which we already have added as we step through it already. And now that we hit this return far function is where it starts getting weird and throws off our debugger. But why is this? This is simply due to the return far instruction that is supposed to pop the return instruction pointer from the top of the stack to the EIP register and pops the following value on the stack into the CS register. This is important since the value that was previously pushed, which we noticed that was 33, will be loaded into the CS register. The CS register in this case is in charge of switching from 32-bit to 64-bit mode, which from what we have talked from previously about how our program is a 32-bit process running on a 64-bit CPU, when a program decides to go to the address that is being pointed to, it will start the execution of code as 64-bit code. This is the reason why our program goes wild after hitting the return far instruction. And 33 is the value that helps the CS register determine if the code will be executed in 64-bit mode or 32-bit mode. And 33 is a value for 64-bit mode, and 23 is for 32-bit mode. So now that we are in this section, we could tell that this is where the instructions start getting interpreted as 64-bit mode, thanks to the obfuscation here. We need to load in all the OP codes of these instructions into this assembler to correctly analyze it. So let's proceed to doing that. So I pulled up an online disassembler diffuse and put in all the OP codes of that section that we need to analyze. And I disassembled it to these instructions here. Now, I have already analyzed this, so I will be bringing in my own annotations and comments to it. So now that we have the disassembled code, here we start comparing all the values that we inputted initially into the key for the program. The first character here gets compared to ASCII H. The second character here gets compared to ASCII 3, the third to 4, and the fourth to V. So now we know the first four characters of our key. After the four comparisons, we now have to add our RAX and RBX registers, which are the values 5 and 6 from our input. And these values that were just added must equal to hex B3 for this comparison for it to be valid. And we could change RAX to be X and RBX to be Y, so we could solve for these values later. Continuing, we have this section. This is where we start determining what our sixth character will be. And it comes down to this comparison to hex 1C. RAX, after these operations instructions, it is x squared minus y, and must equal to hex 1C. Now, after this, after we solved for what the fifth and sixth characters were using these arithmetic operations, we came to find that the fifth character is ASCII E and the sixth character is ASCII N. And then we get to the last character, our seventh character of our key, which gets compared to hex 0, which means no on the ASCII table. This is most likely due to checking that there are no characters present after the first 6 characters of input, which means that our key is actually 6 characters long. Now, if everything goes correct, after checking the key, we set the value to 1 before returning to where we originally checked the EAX value for 0 or 1, which determines if we were correct or wrong. So now that we have this information of H, 3, 4, V, capital E, and N for our key, let's try this and input it. So now we could just run the application once again, input the key that we found, and then press enter, and we get the correct message after inputting, meaning that we successfully reverse engineered this crack me and found the key to be H3, 4, V, capital E, N.
All right, so what did we learn? So a lot, obviously. So kind of what we learned from the first file, right, was just kind of trying to be patient with the debugger. Like from the stuff we've seen, when we went into it, we kind of expected maybe seeing, the password maybe like stored in a register and then kind of see the hex view. But this file was a little different as we kind of got like we did end up loading the correct password into a register, but we kind of loaded it off the stack, so it was a little different.
And as well, we learned a lot over the second crack me that we had, especially the Heaven's Gate technique. We learned how this technique leverages the switch from 32-bit to 64-bit code execution, as well learned even more the how return for instruction manipulates the stack to achieve this switch. Basically just gain an insight into how this technique is used to complicate reverse engineering and obfuscate the program and the debugger. And as well, I just got more comfortable with, assembly code. Coming from not like working too much with assembly, this really like helped me learn and see like patterns inside the code and see what I was supposed to look at. And it definitely helped me become a better reverse engineer and like thinking differently when going into a file that we need to analyze, both static analysts and dynamic analysts. But overall, we did learn a lot, as well the handling of complex execution flows and trying to understand where the program flow was just going to. But yeah, that was and most importantly, we learned teamwork and collaboration.
Yes, sir. Teamwork. Teamwork makes the dream work. All right, so we hope you guys enjoyed the presentation.